Hello, everyone. My name is Kachun Yu, and I am an astronomer at the Denver Museum of Nature and Science. And I want to welcome you to our Science Division Live, which happens every Thursday. And today I want to talk about our own Milky Way galaxy. Our galaxy is a collection of hundreds of billions of stars, of which our sun is only just one member of. And what I'm going to do now is I'm going to transition us to a view of the known universe within a computer simulation. This is some of the software that we run in our planetarium to take our visitors out into space. And so you see the Earth floating in front of us, but what I want you to focus on are the stars in the background. And the Milky Way is normally a very faint band of light that appears in the nighttime sky. And it's usually not really possible to see in Denver just because of all of the light pollution. But if you drive out into the country, way out east into the plains or up into the mountains, you can, and once you get to a really dark site at night, you might be able to see this very faint band that runs across the sky. And here we've really amped up the brightness of the Milky Way. And so what you see is literally hundreds of millions of stars at any given position. And the stars are so faint from the Earth that they appear smeared out into this very faint band. And this band encircles the sky. And in fact, the Milky Way, the name of it comes from ancient peoples looking up into the night sky and imagining the gods spilling milk up in the night sky. And so you're seeing that. But when astronomers started to look at the Milky Way, once we had telescopes, they realized, starting with Galileo, that it was actually that faint glow actually consisted of countless stars. And what's also very remarkable, especially when you have very deep photography, we can see all very faint features, is that very faint band is also actually broken up by dark patches. And you can actually sort of see that there are these darker regions. And those regions are places where it's not that they're devoid of stars, but they are regions where there are dark, dense clouds of gas and dust that are actually blocking the starlight from reaching us. So there are stars behind those clouds, but we can't see them, at least not in visible light. So one thing that we can do is we can switch on a different wavelength of light. And here what I've done is I've switched over to the near infrared. And here you can see that many of the larger dark clouds have actually disappeared. And you still see some kind of brownish clouds. And so what happens is that in the infrared, the infrared light is actually can transmit through some of these darker clouds easier than the visible optical light that our eyes are sensitive to. And so you still get a sense of those dark clouds in the densest parts or in the densest clouds, but many of the less dense clouds have faded away. And we can continue moving deeper into the infrared. And here we've moved into what astronomers call the far infrared. And I've left the stars on just so you can sort of get a sense of where the stars would be. But stars actually don't emit very much light. So I'm just going to go ahead and turn them off at these wavelengths. And at here, the infrared light is actually now sensitive to the emission from the dust. And so these clouds are only about 10 to 20 degrees above absolute zero. So 10 to 20 degrees Kelvin above absolute zero. So they're extremely cold, but and because they still are above absolute zero, they will emit some infrared light. And that's the light that we're seeing. And so here now you can see that dust pervades the galaxy. You still have that band of the Milky Way, but there's dust emission from throughout. Now I'm going to also turn on the constellation lines. And these are, of course, just lines that represent constellations that have come down through us from the Greeks and the Babylonians and the Egyptians and the Arabs. And these are our modern constellations, but of course, every culture throughout history has had their own set of constellations. That's the Great Square of Pegasus that's going off to the right. And now we're coming up on the constellation of Orion, just ahead of us. And you can sort of get a sense of the hunter with the belt and a shield and a sword or a club that he's putting up. And Orion is a region of intense star formation. So the belt of Orion, well, just below the belt is the sword that's hanging on, that's hanging from his waist. And you can see some bright emission directly ahead of us in the center of the screen. And those are molecular clouds that contain lots of star formation. And so let me turn the visible stars back on. And so now we have the great, wonderful Orion constellation. And so those clouds that I was talking about earlier are also locations where star formation can take place. And so what we'll do next is we'll fly out to see our galaxy. And so as we do, you can see that the constellation lines distort, showing that the stars that make up the constellations that we see are not necessarily actually close by to each other in space, but they can actually be spread out by many thousands of light years. But now we're flying out to see the visible galaxy. This is our Milky Way galaxy as seen from outside of it. Now, we've never sent a spacecraft nor telescopes this far, or robotic spacecraft, the ones that are in the process of leaving the solar system. They've barely left the solar system at all. So this is many, many times further away than any of our robotic explorers have gone. So our picture, our visualization of our galaxy is based on our best astronomical data about what the galaxy is shaped like. And you can see that even the stars that make up our visible constellations are only a small portion of the Milky Way. You can see those red lines are a tiny fraction of our Milky Way. Our Milky Way is about 100,000 light years across from one edge to the other. And our sun orbits only about halfway from the center out to the outer edge. And I think I even have an orbital line. So the yellowish circle is a calculated trajectory of the sun's orbit around the Milky Way center. And the sun takes on the order about 220 to 240 million years to orbit once around. And I mean, if you think about it, our Earth orbits our sun once a year, 365 days. That's the definition of our year. And our sun takes over 200 million years. And in fact, the last time our sun was in the same spot in our galaxy, over 200 million years ago, the earliest dinosaurs were roaming the Earth. That's how long ago it was. Now, the glow that you're seeing from the Milky Way is coming from all the stars. And so the glow is brightest at the center. And so that's where the number of stars is greatest. And then the number decreases as you go further out from the center. You also see the spiral arms of the Milky Way that makes the spiral or the pinwheel-like pattern. And these spiral arms are also where the dark clouds are. So you can see the dark clouds of gas that highlight the arms. And so those are the locations where we have stars forming. And in fact, you even see clumps of red along the arms. Those are regions of nebulae where star formation has taken place and the young stars have lit up the gas. And one final thing that we can do is we can tilt the Milky Way on its edge. And you can see that the Milky Way, a spiral galaxy, because of those spiral arms, is actually really thin. It's, the best description that you can make of it is, it's shaped like a plate or a pizza with a bulge of stars out in the center. And so let's fly on back towards the Milky Way, and we can see again the vastness of the disk of the Milky Way, made up of hundreds of billions of stars. And we're going back towards the sun and getting back close to our solar system and where we started off. And here we're looking at Orion, the constellation of Orion again, near the center of the screen. And off to the upper right of Orion is the constellation of Taurus, the bull. And the bull is basically that sort of Y-shaped constellation. It has these two long horns that are pointed to the upper left, just above Orion. And the body of the bull is just a single line emanating from the pair of horns. But very close to those horns is a, let me see if I can find it, is the Crab Nebula. And I'm going to have to turn it on. So give me just a second while I do that. And we can fly up close to it. And so the Crab Nebula is actually the remnant of a star that exploded more than about 1,000 years ago. And we're still flying towards it. Here we go. So this is the Hubble Space Telescope of the nebula. And the star went supernova. So this is a star much more massive than the sun, at least 10 times the mass of the sun or so. And its explosion was noted by Chinese astronomers, as I said, almost 1,000 years ago. And curiously enough, it wasn't noticed by any observers in Europe, although there's some evidence that Native Americans in the American Southwest might have noticed it and recorded it in petroglyphs down in the Four Corners region in Mesa Verde. But the star blew up at the end of its life, and its remnant is what we call a neutron star that's at its center, and which we can still detect to its day. But in the aftermath of the explosion threw out this enormous cloud of debris. And in the process of collapsing and then exploding, the supernova basically created or recreated all the heavy elements in the periodic table. And so it turns out, and then what happened was that this explosion then spewed all these heavy elements back out into interstellar space, where it then can recollect and into the interstellar clouds that we were seeing before in the Milky Way galaxy. And so these heavy elements basically polluted the interstellar clouds, and those clouds then form the next generation of stars. And so the stars that, or our sun, was basically formed out of an interstellar cloud, like the ones that we see here in our visualization. But because the sun had all these extra elements, those elements ended up in the planets and then eventually in life on Earth. So heavy elements like iron and nickel and gold and uranium, and even carbon and oxygen, those were all created in different types of stars and in different end states of stars. And so we literally are made up of stuff that came from stars that was spewed out into the interstellar medium and then recollected into planets in solar systems, like the ones like our solar system, and then eventually found its way into life here on Earth. And so with that, that's a kind of a quick run through or a tour of our galaxy. And memory, if we have any questions from Facebook or YouTube, I'd be happy to answer them. And I can also continue flying around and visiting other places in our galaxy.
Yeah, sounds good. We actually do have a few questions coming in from Facebook and YouTube. So if you're watching on YouTube, feel free to drop your questions there too, and we'll get them to Kachun. So we have one from Crystal who asks, what are the dust clouds in the Milky Way made up of?
Yeah, that's a really great question. What are they made up of? So it turns out that the most common element in the universe is hydrogen. That's out of the Big Bang. Hydrogen ended up being about 90% of the atoms in the universe. Helium, which consists, so hydrogen is the simplest atom. It only consists of one proton and one electron. Helium, which has two protons, ended up being about 10% of the atoms. And then it turns out that, and then there's, out of the Big Bang, there was a negligible amount of other elements. A couple of the elements that are heavier than hydrogen and helium. And so all the other elements that, that are heavier have come from stars, from stars exploding. And so if you look at those dark clouds, most of that material is hydrogen. And but because the universe has been gradually been polluted more and more with heavy elements, with multiple generations of star formation, those heavy elements also make their way into those clouds. And so those clouds not only contain lots of, mostly hydrogen and helium, but a few percent of all the other elements that are heavier. And some of these elements also aggregate or stick together to create what astronomers call dust. And in our ordinary lives, dust is like the dust behind your couch or underneath your bed or in your refrigerator coils. There are these big dust bunnies, but interstellar space, the dust is extremely fine. It's sort of like cigarette smoke or smoke from a campfire. And but that very fine dust is enough to block the starlight. So the even though most of the clouds are made up of hydrogen and helium gas, the opacity or the stuff that actually blocks light in the clouds come from these dust particles that are made up of heavier elements.
Awesome. So we also have two great questions from Mina. Her first one is there an astronomical term for an orbit around the galaxy, a galactic year or anything like that?
Yeah, that's a really good question. I don't think there's really an agreed on term for the galactic year, but I think a galactic year is as good of a term as any. So if you want to call it a galactic year, you can definitely call it that. I guess the one thing about the galactic year is that there is some uncertainty about how long the sun actually takes to orbit around. And so we can say that the galactic year is roughly about 220, 230 million years. But unlike the Earth going around the sun, astronomers still don't quite exactly know how long that galactic year is. And so even though I have a nice set of circles showing the path of the sun around the galaxy, this is basically a calculation made by astronomers. And so this is one sort of estimate or best guess as to what the path of the sun is like, but we haven't fully mapped out our galaxy. So even this trajectory that you see marked by the yellow set of circles, these again are our best guesses, and we don't know exactly what the path of the sun might have been, but it's probably pretty close to this.
Gotcha. Mina may have given us a new vocab word there. I mean, I like galactic year. I think it applies. This second question is, how many stellar mass black holes do we suspect are in the Milky Way? What about magnetars? Do we have those nearby?
Yeah, so we are aware of black holes in our Milky Way galaxy. So black holes are at least the ones that are maybe 10 or 20 or 50 times the mass of our sun, those probably came from stars that blew up. So supermassive stars, and our sun will never become a black hole. It's just not massive enough. But stars that are at least 8 times the mass of our sun will blow up in a supernova, and the more massive ones will end up collapsing into black holes, and I can't actually remember exactly how many of those stellar size black holes we've discovered. It's probably on the order of only a few hundred. And that's just because black holes are very difficult to find. They don't normally emit light. And so the emission that we see from them come from material that has jammed up into an accretion disk that's orbiting the black hole and slowly spiraling in. And that disk heats up and it emits lots of X-rays, as well as possibly visible light and light in other wavelengths. And so oftentimes the black holes that we see are in orbits around other stars where where the light and the X-ray emission is from gas from the outer atmosphere of the binary pair that is spiraling into the black hole. But the galaxy also has a supermassive black hole at its very center. So when we look at this very center of the galaxy, we see this extremely dense grouping of stars. But at its very, very center is a supermassive black hole that's about 4 million times the mass of our sun. And the origins of these supermassive black holes are still somewhat unclear. We know that pretty much every galaxy that we have carefully looked at has evidence of a supermassive black hole. Some of them are 1 billion times the mass of our sun. So some of them are extremely enormous. And we think that their origins are probably not from stars collapsing into black holes, but from very early on in the universe, when much larger structures collapse into black holes. And then the person also had a question about magnetars. Magnetars are extremely powerful pulsars, with very powerful or very strong magnetic fields. And I actually don't really know very much about them, nor about how close the nearest one is to us. But I don't, I'm not aware of any ones that are much closer than, I think, a few thousand light years. So I think we do detect them in our galaxy, but they tend to be pretty far away.
Okay, just we'll take a few more questions. I see 2 more here. We have one from Garrett who asks, so with new heavy elements being introduced into the galaxy, are new planets forming a possibility?
Yes, and that's a really great question, Garrett, I think. And let me see if I can turn on. I have to navigate my menu system, so I'm gonna just turn this on right now. So I'm going to turn off the constellation lines, and these blue crosses, or they look like jumping jacks. These represent just a fraction, maybe a tenth, or 10 or 20% of all the planets that have been, planetary systems that have been discovered in our galaxy. And so we've been discovering large numbers of planets only in the past 25 years, 26 years. So this is a relatively new phenomenon. The fact that astronomers have developed telescopes and instruments that are sensitive enough for us to find planets around other stars. And so far we've discovered more than 4,000 planets in the last 25 years. So that's pretty amazing, the number of planetary systems that have been found. And planets do require heavy elements. And I think early on, astronomers were finding a correlation, so that stars with more heavier elements tended to have planets. I haven't looked at the recent literature to see if that correlation still holds, but there are definitely lots of planets out there. And what's also really exciting is that not only are we finding lots of planets and multi-planet systems, but we're also finding planets where the planets are located in the habitable zones their parent stars. And that means that the planets are orbiting neither too far nor too close for liquid water to exist. And there are some estimates that place, there could potentially be up to 20 billion Earth-like planets in our entire Milky Way that are in the habitable zones of their stars. So there could definitely be lots of Earth-like planets out there, and astronomers are definitely interested in finding evidence of life in those other planets. Although currently we don't really have the technology to find that life just yet, but we think in the next couple of decades, we'll be able to put up telescopes that will have the instruments that are sensitive enough to detect biosignatures, evidence of life in other worlds beyond our solar system.
Wow, I had no idea this many planets had been discovered in the past few years. That's amazing. Wow.
Yeah.
Wow. And how about we let this be our final question from Tony, who asks, how do astronomers break up the galaxy into regions for mapping and description? Do they use the quadrants like in Star Trek?
They sort of do, but not quite. So astronomers do have a, let's see if I can turn this on. There's a grid, and the grid isn't coming on. So let me see if I can, I think the grid is, switch this. Okay, you might be able to see just a really, let me pull away from the sun,
Okay.
but you can see a kind of a blue grid in the distance. And so this grid is basically a coordinate system that astronomers use to map the sky. And this grid is actually based on the Earth's latitude and longitude system, although it's fixed to the sky, it's not fixed to the Earth. So whenever astronomers talk about the position of an object, they use coordinates called right ascension and declination, and that's based on this grid. But if we zoom out and look at the galaxy again, so let's zoom out and so you can see the grid disappear. That's actually a really good question. And what I'm going to do now is I'm going to turn off, let me turn on an annotated image of our Milky Way. And so these coordinates that you see here is what we called a galactic coordinate system. And so this is different from the grid that we saw earlier, but this coordinate system is centered on the sun. And so you can see the sun's at the center, and 0 in galactic longitude is actually pointed towards the galactic center, and 180 degrees is pointed in the opposite direction, or what we call the anti-center. So I can't quite remember the Star Trek coordinate system, but I think the Star Trek one is very similar, where they use alpha, beta, gamma, and delta quadrants. Okay. And so you can imagine that if you divided this galactic coordinate system into 4 quadrants along the 90 degree, 270 degree, 0, and 180 degree lines, you would create 4 quadrants, and you can make up alpha, beta, gamma, and delta quadrants. But I think the alpha quadrant in Star Trek is supposed to be the Federation, and so it's that quadrant should contain the entire Federation. But here, all 4 quadrants meet at where the sun is. So this isn't quite the Star Trek definition of dividing up the galaxy, but it is very similar. So that's a fun question to end
that
on.
was a great question. Yes, definitely. Well, we'll end there. Thank you all so much for watching with us today, this episode of Science Division Live. And thank you, Dr. Kachun. Is there any words that you'd like to leave us with as we take this newfound space knowledge into our weekends?
Yeah, well, I mean, the title of this presentation was Gallivanting Through the Galaxy, and we've done it virtually. But I'm also encourage you, if you have the opportunity, if you live in the city and it's very difficult to see the night sky, I encourage you to drive out or take a road trip out into the eastern plains or up into the mountains and find a really dark spot. And you'll be amazed by how many stars that you can see. So it's just something that I encourage everyone to do.
Awesome. And we will be right back here next week with Science Division Live next Thursday at 12 o'clock. See you then. Thank you for
Take care, everyone. Bye-bye.
Bye.